Welcome to this fourth video lesson on astrophysics and cosmology. By the end of this video lesson, you should be able to do the following. 1. Classify stars according to temperature and color, in other words, spectral classification of stars. 2. Understand and define the term luminosity. You're also going to look at the concept of brightness. And then thirdly, state that luminosity of a star may be estimated from its spectrum. You will also be looking at calculations of apparent brightness and luminosity. So let's first look at spectral classification of stars. So as we've seen, stars have a range of properties. Some are hotter and emit most of their light in the blue region of the visible spectrum. Some are cooler and emit their light in the red region of the spectrum. We've also seen that stars have different masses. Lower mass stars, like the Sun, use the proton-proton cycle for fusion, while higher mass stars use the CNO cycle. We've also seen that some stars are bright and others are dim. So the question then becomes one of classification. How can we group stars with similar properties together? Well, there are numerous ways, but generally accepted methods are to group stars by their color, and thereby their temperature, as well as by the composition of the elements in their atmospheres or their spectra. These two classification systems overlap greatly, as we shall see. So let's look at classification by color. Now, here's a very important table which links the spectral classes, colors, and approximate temperature ranges of stars. So on this side, we have the spectral classification. We have O, B, A, F, G, K, M. Then we have the associated colors. So for instance, an O star would be electric blue, and its approximate temperature would be in the range of greater than 30,000 Kelvin. B stars would be blue, and their temperature range would be between 10,000 to 30,000. Kelvin. Now, when we talk about the temperature range, we are talking about their surface temperatures, not the temperature at the center of the star, which can be millions of degrees Celsius or millions of Kelvin. An A star is a white color, and it ranges between 7,500 to 10,000 Kelvin. An F star is a yellowishy white star, and its temperature ranges between 6,000 to 7,500 Kelvin. G stars are yellow, like our Sun, and they range between 5,200 to 6,000 Kelvin. Then K stars are orange, and they range from 3,700 to 5,200 Kelvin. And then M stars are red, and they range between 2,400 to 3,700 Kelvin. So we can see here that red stars are lower in temperature than what blue stars are. And if we link this back to the electromagnetic spectrum, where we have red, orange, yellow, green, blue, indigo, violet, and as one moves in that direction along the visible range of the electromagnetic spectrum, the frequency increases and the associated energy of the photons increase. We get the same or similar tendency here, that from red to blue we get an increase in the surface temperature. In other words, the star is more energetic. Now, this classification system is known as the Harvard system, as it was developed in the early 20th century at Harvard University by Annie Jump Cannon, and was based on an earlier system or scheme that was developed by Draper. We can use the following mnemonic to remember the order of classification. Only boring astronomers fight green killer Martians. O, B, A, F, G, K, M. Only boring astronomers fight green killer Martians. Now, many new types of stars have been discovered since the late 19th century and early 20th century because of the development in technology. So where in the early 20th century we were only able to use ground-based telescopes, albeit that they were massive telescopes, and they basically looked at the universe in the visible range. We have now moved through to radio astronomy, X-ray astronomy, gamma ray astronomy, microwave astronomy, and then also we've moved into space, where we use space-based telescopes like the Hubble telescope and the more recent telescope that went up into space, the James Webb telescope, which looks at the universe in the infrared range. So therefore we've discovered more types of stars, and so additional classes have been added to take into account these extended spectral types, including the W, which is the Wolf-Rayet stars, which are hot blue emitting stars, and then the cool red and brown dwarf classes L, T and Y, among others. So let's consider classification by spectral class. Stars continuously fuse hydrogen into helium, and stars with higher masses can form the other elements in the periodic table that are heavier than helium by continued fusion. So, for instance, we've seen in heavier mass stars that the CNO cycle dominates, where carbon, nitrogen and oxygen play an integral role in the fusion of matter. And so in these stars, these heavier elements are to be found. So this means that different stars will have different atoms present in their atmospheres, depending on the mass and the type of fusion that is taking place. Now, the light generated by fusion travels from the very hot core of a star and passes through the cooler outer layers of the star. Now, recall from the discussion from Wien's law that the light generated by a star consists of all wavelengths of visible light, and UV and infrared, and would contain the whole visible spectrum. And so we would expect the spectrum of light from a star to look like this, starting in the infrared range, which we can't really see, then red, then orange, then yellow, then green, then blue, indigo, violet, and then ultraviolet. So this is basically black body radiation. However, as so often happens in science, is that when one actually carries out the experiment, one finds a different result. So when the light from a star is passed through a spectroscope, which splits the light into its spectral components, we find that dark lines are observed in the spectrum as seen below. So when we look at this spectrum here, and this is the infrared region, and this would here be the ultraviolet, we actually find missing lines at very well defined values for the wavelength. And so this is known as an absorption spectrum. And so what it means is that some wavelengths of light did not reach the spectroscope and were lost somewhere between the sun or the star and being observed. Now, what has caused this loss? So the outer layers of a star contain many different types of atoms. The electron configuration is unique in each type of atom. Electrons are separated by different energy levels. So if an incident photon has the right energy and wavelength, it may be absorbed by an electron in the appropriate energy level. So if the energy of the photon corresponds with the energy difference between two energy levels within an atom, then that photon could then give its energy to an electron in the atom in a specific energy level. So the electron then gains the energy of the photon and is promoted to a higher energy level. In other words, it jumps a quantum jump to a higher energy level. Now the original photon is removed from the beam of light, or EMR, since it has been absorbed by the atom. And so the dark line is formed at the corresponding wavelength in the spectrum. Now, many stars have the same composition, but the star's temperature affects the intensity of the absorption lines. So a star's absorption spectrum can be used to classify its composition and temperature. Now the classification system is arranged in order of temperature. So for instance, type O stars, and we look here at the absorption spectrum of O stars, they are the hottest, and the temperatures decrease as we go down until we get to M stars here at the bottom. Now the 7 Harvard spectral classes can be further subdivided into subclasses through numerals 0 to 9. So this means that an O0 star is the hottest type O star, and an O9 star is the coolest type of O star. Similarly, a K0 star is hotter than a K5 star. The Sun is classified as a G2 star. Spectral studies show that most stars on the main sequence are composed of approximately 70% hydrogen and 28% helium, with the rest made up of heavier elements. Now let's consider an example. We have a star that emits radiation that has maximum intensity at a wavelength of 6,5 times 10 to the negative 7 meters. What is its surface temperature? And state the spectral classification of the star according to the Harvard system. So lambda 0 equals 6,5 times 10 to the negative 7 meters. Using Wien's displacement law, lambda 0 multiplied by T equals 2,9 times 10 to the negative 3 Kelvin meters. And substituting for lambda 0, 6,5 times 10 to the negative 7 meters multiplied by capital T equals 2,90 times 10 to the negative 3. We get that the absolute temperature of the star is 4,461,54 Kelvin. So now that we know that the surface temperature of the star is 4,461,54 Kelvin, we go now and search for where this temperature would be found on this table. So looking here, we see that we are looking in this range, because 4,461,54 Kelvin is greater than 3,700 Kelvin, but less than 5,200 Kelvin. Therefore, this star is a type K star, which would be an orange color. We're now going to consider luminosity and apparent brightness of stars. Now, when we look at the night sky, as we can see in this image, this beautiful image of the Magellanic Cloud, which comes from the Hubble telescope, we can see there's a huge variance in the brightness of the stars. Not all stars are equally bright. So we're now going to consider why this is. So there are two factors that influence the brightness of a star as seen from the Earth. And the first one is obviously the distance from the Earth. The further away the star is from the Earth, the less bright it's going to seem. And then obviously at the source of the light, the amount of energy radiated by the star. So a star that appears bright might radiate a lot of energy, but be far away from the Earth, and so therefore it doesn't look that bright. So in order for us to understand the brightness properties of stars, we need to define two concepts. The first one is the apparent brightness, which we are going to use the symbol B of a star. And this is defined as the intensity or the power per unit area received perpendicular to direction of propagation at the Earth. So the units are, power is measured in watts, area in square meters, so it's watts per square meter. The second property is the luminosity. We're going to use the symbol capital L for luminosity, and it is defined as the power, energy per second, it radiates, and that radiation would be in the form of electromagnetic radiation. So it is measured purely in watts. So we can see these two are very, very closely related to each other. So the luminosity is in actual fact the power of the star. So that's how much energy is being generated by the star per second. Whereas the apparent brightness is the power per area that is experienced at the Earth or on the Earth. Since a star radiates approximately in the same way as a black body, the luminosity of a star is considered to be the same as the luminosity of a black body, which is given by the following equation. L equals sigma A capital T4, where L is the luminosity measured in watts, sigma is the Stefan Boltzmann constant, which is 5,67 times 10 to the negative 8 watts per square meter per Kelvin to the power 4. The area is the star's surface area in square meters. Now, we assume that all stars are spheres, and the area of a sphere is 4 pi r squared. And capital T, as we know, is the absolute temperature on the star's surface. So this equation shows us that the luminosity is proportional to T to the power 4, to the fourth power of the absolute temperature. Now, since the spectrum of a star is dependent on the temperature, we can use the spectrum of a star to estimate its luminosity. So we can see, or we should be able to see, how much information we can actually get in the electromagnetic radiation that we receive on Earth from sources in the universe. Now, we're going to look here at a little bit of mathematics, which is fine because we are doing AP physics. So imagine a point source of light of luminosity L that radiates equally in all directions. So here we've got a point source. Now, because a star is so far away from the Earth, we can view it as a point source, even though the stars are millions of times the size of the Earth. Because they're so far away from us, they can be viewed as point sources. So we've got a point source that's in the middle of this hollow sphere, and so it would have its entire, the sphere would have its entire interior surface illuminated. Now, here is the radius of the sphere. We're going to use d. So as the radius of the sphere increases, so the surface area will also increase, and the constant luminosity has more surface area to illuminate, leading to a decrease in the observed brightness. So looking here, so if you think of this internal surface as a gigantic screen on which all of the electromagnetic radiation from the point source falls onto, and where we are sitting on this surface, and we are observing an apparent brightness. Now remember, the luminosity is the power generated by the star. Then the apparent brightness is where we are. So let's say we are here. Then what we're going to observe is the apparent brightness. Now the apparent brightness is going to be the power, or the luminosity, divided by the internal surface area of the sphere, which would be 4 pi times the radius squared, which is d squared. So notice that the apparent brightness is proportional to 1 over 4 pi d squared, which, should we say, inversely proportional to 4 pi d squared. Of course, the higher the luminosity, we can see the apparent brightness would be proportional, would have a positive relationship with the luminosity. The more luminous the source is, the more the brightness will be, the apparent brightness, wherever we're observing it. So as I've already mentioned, the stars, except that for the sun, are very far away from the Earth and can be considered to be point sources. Now, the sun cannot be considered to be a point source, because when we look up at the sun, and not that we should do it, but we don't see a point, we actually see a disk, which means that we cannot view the sun as a point source. But the distance from other stars to the Earth, which corresponds to the distance d, would be that of a point source. Because those stars, as I've mentioned, are so far away, they are seen as points. And so the Earth would sit on the surface of an imaginary sphere. And so, as we've already mentioned, that the brightness would be inversely proportional to the distance squared, the distance being between the point source and where we are. So this is a useful formula. The brightness, the apparent brightness, is equal to the luminosity divided by 4 pi d squared. Now, just as an aside, when we look at, for instance, gravity, we look at the force of gravity, we look at it from the model of Newtonian mechanics, then the force of gravity is inversely proportional to the distance squared. If we look at Coulomb's law, the electrostatic force is inversely proportional to the distance between the charges squared. And the reason for that is exactly the same reason as what we have used here, is that when we're dealing with electric fields and we're dealing with gravitational fields, then the equipotentials are a sphere that is at a distance r or distance d from the source. And so because of the fact that the forces fall off in the same way as what brightness would fall off, inversely proportional to 4 pi d squared, because of the surface area of the sphere, we get the same thing in Coulomb's law and universal gravitation. So that was just an aside. So remember that the luminosity is power at the source. It's the power generated at the source. The apparent brightness is that which is perceived, the wattage per square meter at the observer, and the d is the distance between the source and the observer, which would be the radius of that imaginary sphere. So now that we've done this, we can now look at some examples. So let's consider the first example. A star of luminosity 6,3 times 10 to the 27 watts is 7,9 times 10 to the 13 kilometers from Earth. What is its apparent brightness? So the luminosity is 6,3 times 10 to the 27 watts. So L equals 6,3 times 10 to the 27 watts. The distance between the star and the Earth is 7,9 times 10 to the 13 kilometers. But now we need to be careful here, because we need to work in meters. We are looking for the brightness B, and we are going to use the formula that we have just derived. So the brightness equals the luminosity divided by 4 pi, the distance squared. Substituting in for the values, so for L, 6,3 times 10 to the 27 watts. For the distance, 7,9 times 10 to the 13 kilometers. But as I've mentioned, each kilometer is 10 to the 3 meters, or 1,000 meters. And we need to work, this distance has to be in meters. So we need to work in meters. So we multiply by 10 to the 3, and don't forget the square. So this gives us a value for the brightness, the apparent brightness on the Earth's surface, of 8,03 times 10 to the negative 8 watts per square meter. So what does this actually mean? Well, at the star, it's generating 6,3 times 10 to the 27 joules per second, because remember, watts is the amount of energy transferred or generated per second. So at the source, it's 6,3 times 10 to the 27 joules per second. But at the observer, we're only picking up 8,03 times 10 to the negative 8 joules per second per square meter. And the reason for that is the observer is only at a very small area or region on that imaginary surface. So the power, the luminosity, the energy generated per second from the source gets spread out in 3 dimensions, in all directions, in a spherical way into space. When it gets to the Earth is sitting at a point on a huge imaginary surface, and at that point, that's how much energy we get per second for every square meter. Let's consider a second example. How far away from Earth is a star that has a luminosity of 2,1 times 10 to the 28 watts and an apparent brightness of 1,4 times 10 to the negative 8 watts per square meter? So the luminosity is 2,1 times 10 to the 28 watts, or joules per second, and that is obviously at the source, which is the star. The apparent brightness at Earth, or on Earth, is B equals 1,4 times 10 to the negative 8 watts per square meter. And we are looking for the distance in meters. So using B equals L over 4 pi d squared, we can now rearrange so that d squared is the subject of the formula by multiplying by d squared on both sides and dividing by b on both sides. So we get that d squared equals the luminosity divided by 4 pi times the brightness. We now square root both sides of this equation or formula to get that d is now the subject of the formula equals the square root of L over 4 pi b. We now substitute for the luminosity 2,1 times 10 to the 28 and for the brightness 1,4 times 10 to the negative 8 into this formula. And we get that the distance is 3,45 times 10 to the 17 meters. And if we were to convert that to kilometers, we would divide by 1,000 meters in the kilometer, which would give us 3,45 times 10 to the 14 kilometers, which is obviously very, very, very far away.